This video is for OCR A Level Chemistry A, and this is for paper 2, exam 2025. I will go over the predicted topics and questions in paper 2 with some targeted revision. So what to expect in your exam? There will be several questions about analytical techniques like mass spectrometry, NMR, and IR, and they will ask you to identify the structure or deduce the structure of the organic molecule and do your analysis for the different peaks or signals you see. Plan an experiment for sensors, reaction scheme with missing reagents and compounds, and these are the flow chart that come in the exam with missing reagents and compounds. New reaction that you would need to simulate to on another compound to find the product. It's not in every single exam, but it's quite common. Reaction mechanisms, there will be several reaction mechanisms, detailed mechanisms, and finally isomerism. So let's start with the analytical technique, and the first one is the mass spectrometry. What do you need to identify in the mass spectrometry? First, you need to identify the molecular ion peak, which is the peak at the far right of the mass spectrum, and that will give you the mass of your organic molecule. However, the fragmentation is quite common as well to come in the exam. For example, if you have an ethyl fragment, which have a M over Z of 29, the removal of this particular fragment can help you to differentiate between two compounds which have the same molecular formula or the same mass. For example, when we have this aldehyde and ketone in front of us, both of these have the exact same molecular ion peak. However, we can differentiate between them using mass spectrum depending on the fragmentation. So the aldehyde here can lose this ethyl fragment, so we can find an M over Z value for the of 29 in the mass spectrum, while this one doesn't have an ethyl fragment lose. It can lose a methyl from either side, but cannot lose an ethyl fragment. Another example is to differentiate between these two ketones. Not both of them are aldehydes here. So these are two ketones. Again, for the one on the left-hand side, it can lose an ethyl fragment. The one on the right-hand side cannot lose an ethyl fragment. So we can differentiate between these two by the presence of this peak at 71, which is the peak resulting from the loss of a fragment of 29, which is for the ethyl. We cannot find it here for the second one because there is no ethyl fragment to lose. Then moving on to the IR. So what are the most important peaks in the IR? The first one is the carbonyl peak, which we usually see as a strong and sharp peak around 1720 centimeter minus 1. Also the OH peak, and we need to differentiate between the OH that comes from an alcohol and the OH that comes from a carboxylic acid, because the alcohol will be more to the left, so at around 3300 centimeter minus 1, but the carboxylic acid OH is still going to be this broad peak as well, but it's going to be a bit to the right, so around 3000 or 2900 for the carboxylic acid OH. Don't forget about the fingerprint region. That will always be different if you do any small change in your structure. Then moving on to the carbon-13 NMR, what type of information can we get from the carbon-13? The first one is the number of peaks in carbon-13 will give us the total number of chemically non-equivalent carbon atoms. And then we can differentiate between aldehydes and ketones and between the carboxylic acid and ester, the carbonyl groups, because the carbonyl group for aldehydes and ketones will be around 200, 220 part per million, but for the signal for the carbonyl from carboxylic acid or ester will be around 160 to 185 part per million. We can also easily find peaks for the carbon adjacent to an oxygen or carbon adjacent to chlorine. And the carbon-carbon, or the carbon which is adjacent to a carbon, will be at the far right, which is below 20 part per million. Normally, you would use the datasheet that is provided to you in the exam to find the expected chemical shift for the different carbons, depending on their chemical environment or depending on what's next to them. And then the proton NMR. The proton NMR is the most detailed one, and usually the question would come to explain the structure, deduce the structure, and explain the different things that you see in the proton NMR. So in the proton NMR, it can be used to determine the number of chemically non-equivalent protons, which is the number of peaks, and the integration here, the integration value will give us the number of hydrogen ions that give that particular signal. So how many signals we have in the NMR, and the integration will give us the number of protons responsible for each signal. And then the chemical shift, so the chemical shift where we find the signal in the NMR, that will give us data or information about the chemical environment. So we're going to use the data sheet to determine the most probable chemical environment. So whether it's next to a carbon, next to a carbonyl, or the carbon that has the hydrogen is next to an oxygen, and so on. The splitting will tell us how many adjacent hydrogens there are. So the number of hydrogens on the adjacent carbons basically will do the splitting for the proton signal. So if you have one adjacent proton, or there is only one proton on the adjacent carbon, then the signal will be split into a doublet. If you have two, then it's going to be a triplet. If you have three, it's going to be quartet, and so on. So even if you don't figure out the correct final structure, you don't need to worry too much, because your interpretation will get you the most of the mark. So this is a practical example in front of us here. So this is a table with the different chemical shift, splitting pattern, and integration value. We can see that there is a signal here at 1.2. Of course, you're going to use your data sheet to find the most probable chemical environment for this one, but this one, it will be a carbon hydrogen next to a carbon. It's doublet, which means there is only one hydrogen adjacent on the adjacent carbon, and there are three, integration three, so that means there are three hydrogens here that give that particular signal. This one, 2.1 singlet and 3 proton. That means it's, again, it's carbon. The chemical shift will tell us that it's the carbon hydrogen is adjacent to a carbonyl group. It's singlet, meaning there is no adjacent protons on the adjacent carbon. And then the integration value 3 means there are 3 hydrogen ions. You can carry on like this with each of these. You need to give interpretation for the chemical shift, interpretation for the splitting, and then the integration value. Put all of that together to finally find the final structure of your compound. The reaction mechanism. So rule of thumb for reaction mechanism, that curly arrows will go from electrons to electron deficient atom, or towards a single bond to make a double bond. So this is how we move the curly arrow. The curly arrows indicate the movement of electron basically. There will be several reaction mechanisms in your exam, and there will be organic synthesis question and a whole mechanism question, and also plan an experiment. All of these would need your reaction mechanism. So remember that when a bond is added, another has to be broken unless you make a positively charged oxygen or nitrogen with a dative covalent bond. So eventually the compound has to be not charged. So before I go quickly over the reaction mechanisms that you need, or the type of reactions that you need to go over for your exam, I will quickly go over nucleophiles and electrophiles, because they are very important in any reaction mechanism. So a bond is formed when electrons move from a nucleophile to an electrophile. Nucleophiles could be anything that has a lone pair of electrons, like nitrogen with a lone pair, an amine, water, or an alcohol with the oxygen with the lone pair. Or it could be something with a negative charge, like the hydroxide ion or the bromide. Or it could be an nucleophile with a carbon-carbon double bond. So alkenes with the carbon-carbon double bond act as nucleophiles. And the electrons will always move from this nucleophiles to go towards an electrophile or an electron deficient atom. So what are the possible electrophiles? Electrophiles could be a positively charged atom, like hydrogen plus, or it could be a double bond to to an electronegative element. So if we have something like a carbonyl group like this in aldehydes and ketones, the carbon here is electron deficient and it acts as an electrophile. The electrons will move from the nucleophiles toward this one while we break the bond, the double bond between the carbon and oxygen. Or it could be from a single bond to an electronegative element. So if you have something like hydrogen chloride, and then the hydrogen will be an electrophile here, we see that in nucleophilic substitute in the addition reaction to the electrophilic addition to double bonds, where you have the alkene with the double bond of alkenes that will move towards the hydrogen, and the hydrogen is an electrophile, and then the bond will break between the hydrogen and the chloride. So these curly arrows will show the movement of the electrons here. So the movement of electrons from the nucleophile toward the electrophile. And then if we have to break a bond, then we will break a bond, because if a new bond is formed, another bond has to be broken unless your compound is charged. So what are the most important reactions that you need to revise for your exam? The first one is the radical chain reactions for alkanes. This is for chlorination or sometimes bromination of alkanes as well. This is the photochemical chlorination or bromination of alkanes. There are three steps for this reaction. The first one is the initiation, where we use the UV light to homolytically break the bond between the two chlorine or bromine to give the free radical. So this is the initiation. And then the propagation step will be a reaction always between a free radical and a neutral compound to make more free radicals. Remember, when chlorine react with methane, for example, it will always give you hydrogen chloride. If it's bromine free radical, it's going to be hydrogen bromide, and they give you the free radical of the methyl free radical. And then you will carry on creating more of the free radicals. The termination step is when the different free radicals created during the process react together to give you neutral compound. Usually these reactions have so many different products. The CFC and the ozone layer, remember that the ozone layer is essential because it absorbs the UV light and it protects from the harmful UV light. And chlorine free radicals are formed from CFC in the upper atmosphere by under the effect of the UV light. So the CFC will give you chlorine free radical that will react with the ozone to give oxygen and ClO free radical, and then this will react again with ozone to give you more of the oxygen and the chlorine free radical. So it basically makes holes in the ozone layer by breaking the ozone, converting it into oxygen. Nucleophilic substitution reaction, we have three main nucleophilic substitution reaction. The first one is the reaction of alkyl halides with sodium hydroxide to make alcohols. Here, the condition is heating with aqueous sodium or potassium hydroxide. The reaction mechanism is typical. You have the hydroxide with the negative charge. Don't forget the lone pair of electrons on the oxygen. This is the nucleophile. It will attack the carbon here, which is the electrophile, and the bond between the carbon and chlorine will break. We will substitute the chlorine with hydroxide to give the alcohol. The second one is the reaction with cyanide, which is the senses for nitriles. So again, if you have an alkyl halide with the cyanide, and then the lone pair of electrons here is going to be on the carbon with a negative charge. Again, the same thing, it's the same mechanism, and you're gonna end up with the nitriles. The third one is reaction with ammonia, which is for the senses of aliphatic amines. So you start off with the ammonia as your nucleophile. This is not charged now, so it attacks the electrophilic carbon with the bond breaking between the carbon and bromide. Now we make an intermediate with a nitrogen having four positive charge and four bonds with a positive charge, and then another molecule of ammonia will act as a base to take one hydrogen atom from here as a proton, and the electrons move towards the nitrogen to get the neutral compound, which is the primary amine. Elimination reaction. Elimination reaction, we see this in the synthesis of alkenes, either from halogen alkanes. And in this case, we're going to heat with ethanolic potassium hydroxide or sodium hydroxide. So if you heat with aqueous sodium or potassium hydroxide, there will be substitution, but with the ethanolic, you end up with the elimination. In the elimination reaction, you have the hydroxide ion as a base here. So it will come to take the hydrogen from the carbon that is adjacent to the carbon that has the bromide. So once this happens, then there will be a double bond formed here between the two carbons, and the bromide is going to leave. So you end up with the alkene. Another one is synthesis of alkenes from alcohol. This is a dehydration. The condition for that is heating with concentrated sulfuric or phosphoric acid. So in this reaction, it's going to be under acidic conditions. We use the acid here. So the acid in the form of a proton. So the first step is to protonate the oxygen. Again, movement of electrons from the lone pair of electrons on the oxygen towards the hydrogen. And that will make a charged intermediate with oxygen with 3 bonds and a positive charge. That will facilitate the movement, the removal of the hydroxide group in the form of a water, and that will give you another intermediate, a carbocation with a positive charge on this carbon, because this bond is going to break. And finally, the hydrogen on the adjacent carbon will leave to make the double bond, and we regain the hydrogen ion because the hydrogen here ion or the acid is a catalyst. Electrophilic addition reactions, we see electrophilic addition reaction in case of alkenes. This is different from the nucleophilic addition reactions, which see in case of the aldehydes and ketones. So the electrophilic addition reaction, exemplified by the addition of hydrogen halide to alkene. In this case, the nucleophile is going to be the double bond between the two carbons, which is going to attack this electrophilic hydrogen. So the hydrogen will be added first. Of course, the bond between the hydrogen and chlorine will break. So the hydrogen will be added first. This is a symmetric alkene. So the hydrogen can be added to any of these two carbons, and the other carbon will have a positive charge. Now, this positive charge acts as an electrophile, and the chloride that left in the first step will be a nucleophile that will again attack this carbon or carbocation to give you the haloalkane as your product. However, in case of unsymmetric alkene, you can end up with two products. One of them is a major product, one of them is a minor product. This is an example of an unsymmetric alkene. So when the hydrogen is added in the first step, you can end up with two different carbocations. The first carbocation here is due to the addition of the hydrogen to this carbon, and then the second one is due to the addition of the hydrogen to the first carbon here. So, or the carbon to the left. So as we can see, there are two possible carbocations that can be generated. One of them is more stable than the other. So the one which is the secondary carbocation will be more stable. Secondary carbocation is when you have a carbon that has two carbons attached to it, or a carbon with a positive charge that has two carbons attached to it. So it will be more stable than the primary carbocation here, which only has one carbon attached to it. So this, in either case, the bromide is going to attack the cation or the carbon with the positive charge to give you two possible products. However, one of them is going to be a major product, the other one is going to be the minor product. So the minor product here is this one, and the major product is that one because of the generation of the more stable secondary carbocation. I always tell my student that not to make any confusion with them. So when you have two carbons and a double bond and you want to add the hydrogen and the in this reaction, it's unsymmetric. Always add the hydrogen to the carbon that had the larger number of hydrogen atoms. So I always tell them make the rich richer. So when you have a hydrogen that is rich in hydrogen, add hydrogen, another hydrogen to it to make it richer in hydrogen. Another electrophilic addition reaction is the addition of halogens. We're going to follow the exact same mechanism. Instead, in this time, we add to bromide, for example, if we add bromine, or to chloride if we add chlorine. But otherwise, if you don't, then so it will follow the same, exact same mechanism. In this case, you don't end up with two possible products or two isomers or major or minor product, because both the carbocation that will be generated in either case, the final product, whether you're going to have a more stable or less stable carbocation, you're going to end up with the same product because you add bromide on or the same atom on both atoms. The addition of water is called dehydration, and this is for tenses of alcohols. So when you have the alkene and you add water in presence of an acid, you end up with an alcohol. The mechanism for this reaction is quite typical. And in this case, we're going to have the acid that is going to be added first to the double bond. And then we're going to, this when we add water at the end and warm with water, this is going to give us the alcohol. So the mechanism starts with the double bond between the two carbons approaching the hydrogen here, which is the hydrogen on the OH of the sulfuric acid, with the bond between the hydrogen and oxygen breaking. The hydrogen ion will be added, and then that will give us a carbocation. The sulfate ion or the hydrogen sulfate ion that is formed from the first step will act as a nucleophile to attack the carbocation or the carbon with a positive charge to give us an intermediate of ethyl hydrogen sulfate in presence of water and warming that will give us the alcohol. And we will the acid will be regenerated because it's just a catalyst. Here, if you have an unsymmetric alkene, you're going to end up as well with a major and a minor product. So don't forget that to consider that in your answer. Nucleophilic addition reaction to carbonyl group. So this is the addition of cyanide. So when you have a carbonyl group from aldehydes or ketones, as we said, the carbon that is bonded with a double bond to an electronegative atom, it can act as an electrophile. So the cyanide again is going to be the nucleophile and it will add to the carbon. Don't forget the lone pair of electrons on the carbon. There is a negative charge as well. And then the double bond will break because we made a new bond here between the carbon and carbon. And the double bond between the carbon and oxygen will break, will give you a negative charge on the oxygen. In this reaction, you would need to use an acid. So the acid will be a source of a proton. The oxygen with a negative charge will take that proton to give you the hydroxynitrile product or the addition product. The conditions for this reaction is the use of potassium cyanide or sodium cyanide when presence of an acid. Addition elimination reaction, these for acid chloride, esters, or acid anhydrides with nucleophiles. The nucleophiles can be either alcohols, amines, or water molecule. The reaction for this or the mechanism for this type of reaction, as the name implies, there will be an addition step followed by an elimination step. So the first addition step, if we have an alcohol like this one, the first addition step will be the addition of the alcohol to the carbon of the carbonyl group of the acid chloride or anhydride. That will follow by that will be the first step. So there will the double bond between the carbon and oxygen will also break at the same step. That will give you the first intermediate. Don't forget that the oxygen here, when it was added from the alcohol, the oxygen will have 3 bonds now, so it's going to have a positive charge. The next step will be the elimination, and the elimination will be the elimination of the chloride, while the double bond is regained between the oxygen and the carbon. Now, don't forget the positive charge on the oxygen with the extra hydrogen. This has to be removed from using the chloride that left, and that will end up with the neutral compound here, which is going to be an ester. Another example, if we use an ammonia, for example, as a nucleophile, and we used the anhydride in the elimination step or the second step, the bond between the carbon and the oxygen from the second carboxylic acid of the anhydride is going to break, and then that will give us the final product, which is an amide. Don't forget that the mechanism is exactly the same, it's just a different nucleophile. Esterification is the formation of esters from acids and alcohol. So these are various examples when you use different acids with different alcohol to make an ester. This is very common in your exam, especially in these flow chart where they ask you to find the product. So they give you a compound that has a carboxylic acid functional group, for example, and on the reagent arrow, there will be an alcohol and an acid, and they ask you to find the final product or the missing product. So the product is going to be an ester. Hydrolysis is the formation of alcohols from ester, so it can be either acid catalyzed hydrolysis or it could be base catalyzed hydrolysis. So if you have an ester in presence of an acid and water, you can end up with the carboxylic acid and the alcohol that form that ester. Or if you use a base, then you're going to end up with the salt or the anion of the carboxylic acid and the alcohol. Another hydrolysis is the hydrolysis of the nitrile group or the cyano group to give the carboxylic acid. So if you have a nitrile group like this, and then the condition will be the hydrolysis use of water with an acid, that will give you a carboxylic acid as well. So this is another hydrolysis type of reaction. Electrophilic substitution to benzene ring. So in electrophilic substitution, you're going to have an electrophile with a positive charge. The mechanism is typical here. So the electrons from the ring will go towards the electrophile, and then you're going to have this unstable intermediate where you need to draw the ring of the electron as an open ring with a positive charge around the carbon atom where the electrophile was added. And then the next step will be the removal of the hydrogen as a proton, and the electrons from this bond go back inside the ring to make the regain the aromaticity of the benzene ring or the full electron ring inside the benzene. And this is the rapid step in the reaction. Examples of these from your specifications are the halogenation. In the halogenation, you're going to use bromine in presence of a catalyst like iron bromide, and that will generate the electrophile, which is the bromide with the positive charge. And then this is going to be the electrophile that attacks the benzene ring. And then we have another example, which is the Friedel-Crafts acylation or alkylation. Here we're going to use either an acyl chloride if it's acylation, or we're going to use an alkyl halide in presence of a catalyst, which is the aluminum chloride. In either case, the aluminum chloride will play a role to generate the electrophile. The electrophile is the acyl electrophile here, where the chlorine atom or the chloride here is removed, and then we're going to end up with a positive charge on the carbon, and this is the electrophile, and this is the and the chloride will be attached to the aluminum chloride, which is going to be regained at the end because it's just a catalyst. If we use for alkylation, if we use an alkyl halide like RCl, then with the aluminum chloride, you're going to end up with the R with a positive charge, which is basically your electrophile. The reaction mechanism is again exactly the same for the electrophilic addition. This is just an electrophile attacked by the electrons inside the ring, making the unstable intermediate compound. And then finally, the hydrogen is removed and you get your final product. You're gonna get this acyl benzene in case of acylation, or you're gonna get an alkyl benzene like that, just an R here if it's methyl. So it's gonna be methyl benzene here if it's alkylation. Nitration is another example of the electrophilic substitution for the benzene. The catalyst for this is a mixture of nitric acid and sulfuric acid, and this is the reactions of how the electrophile is generated, which is the NO2 with a positive charge. The mechanism is typical with the electrophilic substitution, but the electrophile here is the NO2 plus. Reduction, we have two types of reduction. The first one is reduction of cyanides to make amines, and the cyanides can be reduced either using reducing agent like sodium borohydride, and that will give you primary amine, or you could use nickel catalyst with hydrogen at high temperature and pressure also to give you primary amine, or you could use the reduce the aromatic nitro group to give aromatic amine. So if you have an aromatic nitro group like this, with in presence of tin and concentrated hydrochloric acid under reflux, that will give you the amine, the aromatic amine. The second step for this one is to use the sodium hydroxide, because what comes out from the first step will be the quaternary ammonium salt. Phenols, so the phenols are these compounds which are aromatic and have an OH on the benzene ring. These are the phenols. The type of reaction you need to know for the phenols is the bromination step. So with bromine, the phenol will give you the tribromophenol, and the position of substitution will be on carbon 2, 4, and 6. Reaction with nitric acid for phenols will give you either the two nitrophenol or four nitrophenol, give you a mixture of these two. It's not going to be tri-substituted like with the bromine. Directing effect. So remember the directing effect of both electron donating and electron withdrawing group. So for electron donating group like OH and NH, they will direct the electrophile to position 2 and 4 of the benzene ring. So you have here the phenols, and the phenol has an OH group, which is an electron donating group, and this will direct the electrophile here from the bromine into position 2 and 4. What happens is that the lone pair of electrons on the nitrogen or oxygen will be delocalized inside the benzene ring, and that will increase the electron density in the benzene ring, making it less stable and more susceptible to attack by the electrophile. While electron withdrawing group like nitro group, the directing effect will be to position 3 and 5. So if you have a nitrobenzene, for example, like this one, and you do a reaction, then you're going to end up with a substitution in position number 3 and number 5. Organic chemistry, synthetic schemes, you're going to have these flow charts, one or two of these flow charts in your exam with missing reagents and missing products. How can we answer these type of questions? First of all, you need to think of the role of the reagent, and then look at the functional group, look where the change in the product is, and think about how to make that particular change. So let's have a particular example from one of the past papers. So now we have this starting material, which has a carboxylic acid group and an OH group. And then what they bought here as reagent, they bought an alcohol and sulfuric acid. So when you have an alcohol and sulfuric acid, so which functional group is going to react with the alcohol? Of course, it's the carboxylic acid group. So we're going to end up with an ester here. So you need to give the ester from the reaction between this carboxylic acid and this alcoholic function group. And then on the second one, they bought a carboxylic acid with a sulfuric acid as a catalyst. So now which one is going to react? Always look at your functional group. So it's going to be the alcoholic functional group that will react with the acid to give us the ester. And if we look at this one, so this is the first starting material, which have a cyano group. This is a cyanohydrine and OH. And then the product here, what the change that happened? The only change is the change of the nitrile group into a carboxylic acid group, because the OH is still the same. So how can you convert the cyano group into a carboxylic acid? This is the hydrolysis of the cyano group, which is by the use of water and acid. And then here they give you only the reagent, which is sodium borohydride, and the product is the 2-hydroxy butanoic acid. So they want you to think of the starting material. This is a reducing agent. Let's have a look at the structure of your product here, which is the 2-hydroxy butanoic acid. What can be reduced? The only thing that comes from reduction would be this alcoholic functional group. So because the carboxylic acid is not a reduction product, but the alcohol is a reduction product. So what can be reduced to give a secondary alcohol? The carbonyl group. So you're gonna have a carbonyl group here instead of this OH. So in your product, in this in your starting material here, you're gonna have this in addition to the carboxylic acid and the CH2CH3. Remember that your reactions are either substitution, addition, or elimination, or hydrolysis. So always think about what type of reaction that is. Think of whether your compound is aromatic or aliphatic. Here, everything is aliphatic. If it's aromatic, then we need to consider the aromatic type of reaction. Think of it whether it's polar or nonpolar, because with the polar compound, we are looking at the functional group, and then everything happens on the functional group, basically. Sometimes they give you a new reaction you never seen before and ask you what would the product be. So how to answer these ones? You need to check the changes in the represented example or in the represented reaction, and then what happens to the functional group. So this is an example from one of the past papers. So here we have this double bond with the use of the ozone. Then what happened? They broke this double bond and added two oxygens to each. So now we're going to apply the same here. So all what we need to do is to break the double bond, replace these with oxygen, carbon-oxygen double bond. In this case, in this one, we're going to end up with two products, but with this one, we're going to end up with one product because it's a ring. So when you break the ring, you're going to end up with an open structure with two carbonyl group, one as a ketone, one as an aldehyde for this one. So all what you need to do is to simulate, so it's just the same reaction with different R groups. Plan a synthetic experiment. This is one of the typical questions in paper two, how to answer. First of all, if they ask you to find the mass of the starting material, how much you're going to use from the mass, and they give you the yield and they give you the mass that need to be obtained from this particular reaction, then you would need to calculate the mass needed from the starting chemical based on the yield. So the mass obtained from the product over the yield will give you the theoretical product mass. You can calculate the number of moles of the product and the same you need to calculate the number of moles of the reactants based on the number of moles of your product. The mass of the reactants will equal the moles times the MR if you need to calculate the mass of your reactant. Use your knowledge of the different reactions to show the reagents used and the conditions for the different reaction or synthetic procedure you're going to apply. Don't forget to write your equation. Normally, it's a long question, and they want you to write your equations as well for each step. And don't forget to refer to purification. So how to purify your organic molecule. If you have water-soluble impurities, you're going to use a washing step where you add water to remove these impurities. When you have an organic layer at the end, you would need to use a drying agent to remove any excess water. Normally, we would use anhydrous magnesium sulfate or sodium sulfate. Use separating funnel to remove water-soluble impurities from the product. So after you add water to your organic product, you have two layers that you need to separate, and then you can mix them using the separating funnel and separate the two layers. Remember that volatile liquids can be purified by distillation. And if the boiling point is in a closed range, you would use fractional distillation instead of the simple distillation. Don't forget about the crystallization or recrystallization step at the end as an extra purification step. And don't forget about the melting and boiling points that can be used as a good indicator for purity, because impurities will decrease the melting point of your product and will make the product or the compound melt over a range of temperatures, and they will increase the boiling point. Polymers. So normally they will ask you about polymers. They will ask you to draw a proposed polymer structure or meeting unit of a certain polymer for both for addition polymers and condensation polymers. So the addition polymers will be for alkenes, and the condensation polymerization is when water molecule is removed either by using a carboxylic acid with an alcohol or an amine with a carboxylic acid to make an amide. And naturally occurring polymers, these are the proteins and DNA. These are all the chemical tests that you need to know for paper two. So these are the different functional group and the chemical tests. So we have the aliphatic alcohols, phenols, unsaturated aliphatic hydrocarbons, aldehydes, ketones, and carboxylic acid. So bromine water test is quite specific. It's specific for the phenols because it will give you white precipitate and will decolorize the bromine. Well, and for the alkenes, because it will just decolorize the bromine water, everything else will not give you any observation for this test. And then the use of potassium dichromate, acidified potassium dichromate test. You're going to have a positive test, which is the change of the color from orange to green. This is for primary and secondary alcohol because this is an oxidation reaction. And it's going to be negative for the tertiary alcohols because they cannot be oxidized. Also for the aldehydes will give you the same color change for aldehydes, but for phenols, unsaturated hydrocarbons or alkenes, the ketones and carboxylic acid will give you a negative test. Tolan test is specific for aldehydes only. It will give you a silver mirror the 2,4-DNP or 2,4-dinitrophenylhydrazine. This is specific for both aldehydes and ketones. Both of them will give you a precipitate. The precipitate will vary in color depending on the structure of the aldehyde or ketone, from yellow, orange, or red, and it can be separated and compare the melting point to database to check the purity or to check the structure of your compound. Everything else will give you a negative results because none of them will react with the 2,4-DMP. Sodium carbonate test is specific for carboxylic acid fizzing with the evolution, or the you're going to have the fizzing of carbon dioxide gas. So you can test for carbon dioxide with lime water. Sodium hydroxide, it reacts with the phenols. So phenols react with sodium hydroxide, and also the carboxylic acids will react with sodium hydroxide. Isomers, so there will be several questions about isomers. Don't forget about the structure isomers, where the you have the position isomer, functional group isomers, and chain isomers, and most the stereoisomers. Then, so we have the D and E isomers of alkenes. So in D and E isomers of alkene, if you have the two groups with the highest priority on the same side, it's going to be the Z isomer. If you have the two groups on the higher priority on opposite sides, it's going to be an E isomer. Remember that when you compare the priority on each carbon around the double bond, you need to look at them atom by atom. And also you compare the atomic number, not the atomic mass. So the one with higher atomic number will take the priority. The optical isomer SNR optical isomers, they rotate the plane polarized light in opposite direction, and this is how we differentiate between them. They are non-superimposable mirror image. Sometimes they ask you to draw the two stereoisomers of the chiral center or of a chiral compound, for example, like this one. Or what you need to do is to put the 4 different groups around the chiral carbon, and then draw the mirror image for it. So you're going to end up with the non-superimposable mirror image, or you're going to end up with the two isomers. Remember that the amino acids are chiral as well. They have chiral carbons, so except for glycine. So the chiral carbon here is the one that has a carboxylic acid group, has an amino group. It has a side chain, which is R. So this R will differ depending on the amino acid. And then it has a hydrogen, glycine, and the first amino acid, which has 2 hydrogens, so it's not chiral. Sometimes in the exam, they ask you to find how many chiral centers are there in a certain compound. So the chiral center has to be a carbon atom. It has to have only single bonds, no double bonds at all. It has to have 4 different substituents, and it can be a part of a ring. So let's have a look at this structure, trying to identify how many chiral centers there are. This carbon is not a chiral center because there are 2 methyl groups which are identical. So now let's to see. So this one is a chiral center. This is a chiral center. This one is a chiral. This one as well. This one, these are all part of a ring. This one, and that one. So see how many chiral centers there are. All of these ones are not chiral because there are 2 hydrogens in each carbon. This one as well, there are 2 hydrogen. This one has 2 hydrogen. This one is not chiral because it has a double bond.